Hello, today we are going to talk about perpendicular lines. In the geometry book, this is chapter 3, section 4. Our objective is to prove and apply theorems about perpendicular lines. Vocabulary, two of them. One of them is more of a phrase. The perpendicular bisector, and then the second one is, distance from a point to a line. So the perpendicular bisector of a segment is a line perpendicular to a segment at the segment's midpoint. That's very important that you know that it's at the midpoint, because you remember the definition of midpoint means that you have two congruent segments. The shortest segment from a point to a line is perpendicular to the line. This fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. So if you're ever asked to give the distance from a point to a line, it's that perpendicular distance because that is the shortest. Here's how to make a perpendicular bisector. Now, you did this in chapter 1. In your project for chapter 1, you were supposed to make a drawing, and one of the things you were supposed to do was a construction for perpendicular bisector, because that's the way that you bisect a line, is by making its perpendicular bisector. So it's not really that hard. You get a compass, you open it up so that you can put the pointy part on A, and then you open up your compass so that it's more than half as long as the segment, and you just swing an arc. Then you leave your compass the same width, the same setting, and you put the pointy part on B, and you swing another arc. The two arcs will intersect, and that point D and C where they intersect, you just draw a line going through those 2 points. And that means that you have a perpendicular bisector. And if we call the intersection of those two lines, let's say O, then AO would be equal to OB, because they would be congruent segments, so they would have the same length. All right, in this example, we're going to name the shortest segment from point A to BC, and BC is a line. See the line? And they'd give you 3 segments to choose from. We could choose AC, AP, or AB. Well, the shortest segment is the perpendicular to the line one, so AP, because the distance from a point to a line is always defined as the shortest segment is always the perpendicular segment from that point to the line. When they ask you to solve an inequality, what they want you to do is to say that, well, that length of 12 is less than the length of AC, which is x minus 8. Or in other words, AC is greater than AP. So we'll just substitute in what we know for both of the lengths. X minus 8 is greater than 12. Add 8 to both sides, and you get that x is greater than 20. So we know that this length here of x has to be greater than 20. So 21, 24, 38, but it would be greater than 20. Okay, here's another example. This time we are asked to find the shortest segment between point A right here and segment B, or line BC. So is it x minus 5 or is it 12? Well, you pick the segment that is perpendicular to the line, and the segment that's perpendicular is the x minus 5. So then we will write that AC is greater than AB. And then you substitute, and 12 is greater than x minus 5. Add 5 to both sides, and our inequality would be that 17 is greater than x, which is the same as x is less than 17, so you would have to pick a value less than 17 in order to make this be a true statement. Okay, we have some theorems in this section. The first one, theorem 341, says that if you have two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So let's look at that again. If you have two lines that intersect and they form a linear pair, so two angles right next to each other, that are also congruent. Well, if they're also congruent and a linear pair, they must both be 90. So that means then that you have perpendicular lines. Okay, the perpendicular transversal theorem says that if you have a transversal, in this case that's Q, that is perpendicular to one of the two parallel lines, then it's automatically going to be perpendicular to the other one as well. So if you know it's perpendicular to one of the parallel lines, it'll be also perpendicular to the other one. And the last one says that if two coplanar lines are perpendicular to the same, this T, this transversal, then the two lines must be parallel to each other. So if you're given that both of these R and S are perpendicular to the transversal, then we know that R is parallel to S. Okay, let's do a little proof about these lines. So we know that R is parallel to S. We should draw then little arrows to show that we know these lines are parallel. Angle 1 is congruent to angle 2, so we can also show that they are congruent. And then we are going to prove that R is perpendicular to T. So the first thing that we would do is set up our table, statements and reasons, and put our given in. We know that R is parallel to S. We know that angle 1 is congruent to angle 2. That's our given. That's done. I'm going to mark my diagram again because I turned the page. And I'm going to mark those things that I just wrote down. Angle 1 is congruent to angle 2. Well, look at the picture. I know these are parallel. What kind of angles are 3 and 2? What is their relationship to each other? What do we call those kind of angles? We call them corresponding angles. And corresponding angles, if you have parallel lines, corresponding angles are congruent. That's the corresponding angles postulate. So that's good. So now we've got that angle 1 is congruent to angle 2, and also that angle 2 is congruent to angle 3. It looks like maybe we could jump over the angle 2's and use the transitive property of congruence to say that angle 1 is congruent to angle 3. Well, if angle 1 is congruent to angle 3, I'm going back to the lines. Look at, if two intersecting lines form a linear pair and of congruent angles, then the lines are perpendicular. There's not a nice way to write that one though. So that's the theorem that we're going to use. Two intersecting lines form a linear pair, and in that linear pair both of the angles are congruent because they're both marked congruent because we found that out. So that means that we have perpendicular lines. So there you go, all proved. Okay, there's more than one way to write a proof. I want to look at this example, which was on will be on your homework. What do we've got here? We've got that M is perpendicular to N. That's our given. So of course we will start out by writing M is perpendicular to N. And we want to prove that angle 1 and angle 2 are a linear pair of congruent angles. So how are we going to do that? What we're going to do is first figure out what does it mean to be perpendicular. So in order to be perpendicular, that means that the measure of the intersection of the angles is 90 degrees. They intersect at 90 degrees. Sorry, I wanted to grab my book. So we have that. We also know, let's see, do we have any other givens? No other givens. But we know that is this pen going to work this time? We know that the measure of, yes, it is working. Measure of angle 1 is going to equal 90 degrees. And we also know that the measure of angle 2 is equal to 90 degrees. Because they're perpendicular, so they must be 90 degrees. All right. Angle 1 is congruent to angle 2. How do we know that? Because look, we said that they're both equal to 90 degrees, so therefore they must be congruent to each other. That's the definition of congruence. Or congruent angles if you want. If they have the same measure, then they're congruent to each other. Then we can use the addition property of equality to say that, well, measure of angle 1 plus measure of angle 2 is equal to 180 degrees. I just added them together. And then finally, the definition of linear pair says that if you have supplementary angles, then they are a linear pair. And that's what we have here. So then our final statement would be angle 1 and angle 2 are a linear pair. And we already proved that they're, right here, we proved that they're congruent to each other. So we finished our proof. Step 3, we had to kind of put it in there because of that of congruent angles part. All right, that's one way to do that proof. But there's more than one way to do a proof. So let's look at this one. I already put all the steps in this one, but I did this one a little bit differently. So I started out with the given, same exact problem, same sketch, everything. And then I said that measure of angle 1 is 90 and measure of angle 2 is 90 because of definition of perpendicular. That means then that angle 1 and angle 2 are right angles, because that's the definition of right angles. If they're equal to 90 degrees, they're right angles. Well, the right angle congruence theorem that we learned in the end of chapter 2 says that all right angles are congruent to each other. So angle 1 is congruent to angle 2. That's where we got that they're congruent. And then I'm going to go back to the whole step 2 here. Step 2 was that the measure of both of them were 90, so I added them together to get 180. That's the addition property. And then angle 1 and angle 2 are a linear pair. That's a definition of linear pair of congruent angles, because of step 4 this time is when I said that the angles were congruent. So I did different things, ended up with maybe one more line, but I still ended up with a valid proof. And I did it one more time. This one's a little bit flawed, but it would probably work. Okay, look at this one. I said, okay, got the given in there. I got perpendicular lines. I said that the measures of each of them are 90. That's the definition of perpendicular. And then I just went right to, I added them together. I did the addition property. And then I jumped to angle 1 and angle 2 are a linear pair. So what am I missing here? I'm missing the of congruent angles. This part. Whoops. So I didn't address the fact that they have to be congruent angles, but I could do that in step 2. I could say, I could do one more line that says if they have the same measure, then they're congruent. But then I'm going back to, I guess, the first proof. So I just wanted to show, and I wouldn't mark this proof wrong, just because you didn't make a separate line for congruent angles. So by doing this, I just wanted to show you that there's more than one way to write a proof. There's more than one way to write a good proof. And some of them you'll use different theorems. Some people will, and some of you will, do things a little bit longer. Some will find the way quicker. And that doesn't mean that your proofs are wrong. All right, this one asks you to do a proof as well. It looks crazy, so we'll just kind of take it step by step here. It says that angle EHF, oh, that's already marked congruent, is congruent to HFG. So we've got this one is congruent to this one. Okay, so if that was not marked, we would have marked it, but it's there. So this angle is congruent to this angle. We also know that FG is perpendicular to GH. That's why there's a, whoops, that's why we have a right angle thing marked here. I guess it does not want me to use my pen. So we are going to write our first thing is our given, and we'll just put down the congruent angles part first. Then from that, if we have congruent angles there, we can say then that if those two angles are congruent, their alternate interior angles, if you look at this as being, no, I can't use my pen. If we look at this as being our two lines here and here, and they are connected with this transversal here, these are alternate interior angles, and they're congruent. So we can use the converse of alternate interior angles theorem to say then that line EH is parallel to FG. We already knew that FG was perpendicular to GH, and we're trying to prove that EH is perpendicular to GH as well. So now we can use the theorem that says that if you have parallel lines and one of them is perpendicular to the transversal, then so is the other. So they're both going to be perpendicular to HG or GH. This is just an example of how you could use parallel and perpendicular lines in kind of a real-world application. It says a carpenter's square forms a right angle. A carpenter places a square so that one side is parallel to an edge of the board and then draws a line along the other side. Then he slides the square to the right and draws a second line. Why must the two lines be parallel? Because they're both perpendicular to the same line. So it's a theorem that you learned that if they are perpendicular to the same line, then they are parallel to each other. In this example, a swimmer who gets caught in a rip current should swim in a direction perpendicular to the current. Why should the path of the swimmer be parallel to the shoreline? So they show the shore, they show the rip current, and they say that you should swim, they should both be perpendicular to the current, so they should be parallel to each other. So, I don't know, the real world ones are a little bit tricky to read sometimes, but they're just looking for which theorem would make this be true, basically. Okay, just a couple more problems to do. In these problems, it shows that we have parallel lines and we have that a transversal is perpendicular to them. And we see that this angle here is 6y, and the other angle is marked 5x plus 4y. So there's more than one way to start looking at this. We could say, okay, we have 6y is equal because they're corresponding angles. We could say 6y equals 5x plus 4y. That's true, but we kind of have to go in a circle then. How are we going to solve for y if we don't know what x is? Or how can we solve for x if we don't know what y is? So instead of doing that, start with right here. If these lines are perpendicular, then we know the measure of 6y. It must be 90 degrees. So start with the simplest thing that you can find. And then 90 divided by 6 is 15. So y is equal to 15. Now that we know what y is, we can say, oh, wait, if you have parallel lines and one of them is perpendicular to a transversal, then so is the other. So this is also perpendicular. So that means that 90 is also equal to 5x plus 4y, but now we know that y is 15. So we're going to solve this for x. So in this case, first we solve for y because that was equal to 90, or 6y was equal to 90. And then we got 15, and then we're going to plug that into the other expression. Minus 60, so we get 30 equals 5x, divide by 5, so 6 equals x. So we found both of our values, and then we know we're done. Let's look at b. It looks bad, but it's really not that bad. We see that this angle is x plus y, this angle is 2y, and this is x. We have two lines that are perpendicular to the same line. That means that we know they're parallel to each other using the theorems we learned in this section. So let's see, they're parallel. What else do we know? We know that I want to use alternate exterior angles, and I guess I will. I'll use the other line here as the transversal now that I know these two lines are parallel, and I'll say that, well, x plus y and 2y are equal to each other because they're alternate exterior angles. All right. I also know that, let's see, x plus y plus x is equal to 180 degrees. How do I know that? Well, they're forming a linear pair. So we can't solve either of these real easily for a missing part, but let's see if we can do a little system of equations here. I'm going to work with this second one, and I'm going to combine my like terms and get 2x plus y equals 180. And then in the other one, I'm going to get my y's on the same side. So I'll subtract 2y, and I'll get x minus 2y is equal to 0. So they're not set up for elimination yet. I guess I could have used substitution, maybe easier. But I'm going to go ahead and multiply, let's see, I'll multiply the top one by 2. Let's see what we get. So that would give me 4x plus 2y is equal to 360. And now I'm going to add these two equations together. 1x plus 4x is 5x, minus 2y plus 2y is gone. 0 plus 360 is 360. Okay, take 360 divided by 5, and we get 72 degrees for x. Now, does that make sense? Does that number make sense? Yeah, because that's x degrees, so that's an okay thing. Now we have to plug that back into one of our expressions to try to figure out what the other one is. What would be the best one? How about this one? It said that x plus y plus x equals 180, and then I combined and got 2x plus y equals 180. But now I know that x is 72. So 2 times 72 would be 144. And then subtract 144 from both sides. So that's what, 36? So y is equal to 36. Which means that this would be 72. That would be an easier way to do this probably. No, that can't be 72. Because that would mean these two are congruent to each other. And that wouldn't make sense. So did I make a mistake somewhere? Let's see, this expression was x plus y, so that's 144 plus y equals 180. I made a mistake somewhere. Where is my mistake? X plus y equals 2y. Yeah, these are alternate exterior angles, right? So I'm trying to find my mistake because this doesn't make sense. My answer doesn't make sense. So when I subtracted 2y from that, I bet that's where I made a mistake. Yep. It should have been x minus 1y right here. So I took minus 2y minus 2y, and I would have 1y minus 2y would be negative 1y. So there's my mistake right there. So let's see how much I can erase without completely starting over. And this I wouldn't need. I don't think that I will have to multiply by anything. I think I'll be able to just add them together and make an easier problem out of it anyway. So 72 is not right. Okay, so I had x plus y equals 2y. That's true, and I subtract 2y from both sides, and it becomes x minus y equals 0. And then the other one was 2x plus y equals 180. I can add these together right away, and I get 3x equals 180, and x is 60. See, even teachers mess up. And now that I know what x is, I'm going to plug it back into the easier one here is x minus y equals 0. So that means 60 minus something equals 0. You can probably guess that the answer is going to be 60. So y is 60 and x is 60. Now that makes sense because that means this is 120 and this is 60. And they should be supplementary like that. And then this one would be 120, so then 120 and 120 are congruent. Okay, there. That's the end. I finished it. Thank you. And this one is not on your assignment. The first one is. This one I thought looked a little challenging, and I was right. Have a good day. Please remember to ask me for help if you need it. Thank you.